Hello, this is lecture 13. In this lecture, we are looking at the power considerations in linkages, and we'll get to realize in a second that actually these power calculations will depend on the velocity analysis would have done previous to these calculations. All right, so in fact, to start looking at the power required, we think of a method called the virtual work method. And this method looks at the sort of the change of work in a system like such as a structure or a linkage such as this one. And let's see what this means. And in fact, the method says like the sum of virtual or infinitesimal works done on a system due to the presence of external effects can be forces or torques which are associated with some virtual displacements. This sum is equal to be 0. And let me explain a little bit here because I don't think this will be clear enough, right? So let's say if the crank rotates a little angle here, let's say delta theta 2. So this angle is delta theta 2. So now point A is going to move to this new position, A dash, and then point B would possibly move to another position here, type thing. So this is B dash, and there is a distance between them. This displacement is going to be delta xb, right? So this from my velocity analysis, I know that I have some displacements. We actually looked at this in the context of computational kinematics, this infinitesimal sort of displacements. Now, let's say I have point C, and point C moved here, C moved to C prime. So if it was initially here as point C, it has now moved to another position, and this is C prime. And the distance here, I can call this D, let's say we can call this DRC, where RC was in fact this vector here, which relates point C to the origin O2 type thing. So this was RC, right? So if this little distance here is equal to H or something like that, let's say this is equal to H, and then RC in fact is equal to R2, which we spoke about before, plus H A J theta 3, or I can write here R2 plus RC relative to A that we discussed before, and this C relative to A, this specific term is this term here, that's RC. So there will be a small change in that, which is delta RC, right? So this is going to change by delta RC. So RC will be equal to RC plus delta RC when the change happens. I'm talking about this. Exactly like XB is going to change, will be XB plus delta XB when things change, and theta 2 is theta 2 plus delta theta 2. Those are small changes in the position of different things. And let's say I have forces acting on the system. So if I say, for example, on the crank, I have a torque acting like that. And then let's say point C has some force acting on it. Let's call FC or whatever. So that's moving with the system. And let's say this here, I have a force FB acting at this point. So now due to those forces, so each force, as you see, is associated with some deflection. And if you multiply a force by deflection, the units would be, let's say, if multiply FB times delta XB here. What sort of units will get? Newton times meter, which is joule. So that's really energy or work, if you like. Okay, so when a force associated with the little deflection will give us work. So this is the method referred to this as delta U at point B. So this is the work existing at point B due to an external force, right? So the method looks only at external forces, does not at all take the reaction in links into consideration because the reactions in different links sort of appear in pairs and positive and negative. They sort of cancel each other in terms of work, right? Over here also, if I take like the torque, if I multiply the torque by delta theta, right? So same if I repeat this method, the time delta theta, this way of thinking, uh, torque is Newton meter and theta is dimensionless. The radians is not a dimension that we consider in engineering. So this here is also joules. So this is also, if you like, infinitesimal work, which is happening at link number 2. I can say this is here due to U, for example, theta 2 or something like that. Just give it a name. So those are all infinitesimal works. And then also I have FC if I multiplied by DRC over here. So don't forget this also is going to be Newton meter as well. So that's Newton meter. So I can say this is another work delta UC, right? Okay, so just now thinking quickly more than anything, and then I will apply the method in a proper fashion. Now, the method says, the virtual work method says, all those infinitesimal works that result from external forces and their associated virtual displacement, which our infinitesimal displacement in our linkage, those produce work, and the sum of all those delta U is equal to 0, and this is what the method actually says. So it's like in here, delta UB plus delta U theta 2 plus delta UC, all this will add up to 0. Okay, so this is the crux of the method, right? Now, the way I applied this here is like I need now to explain the method properly. This is just the concept more than anything. You have to say this is a concept because when we apply the method, we need to be clear on a few aspects and need to clarify this equation and write it proper. So here I need to say that how to calculate the torque or how to calculate the work associated with a point. In fact, the work is equal to delta UB. The proper way to calculate it is not by just multiplying a scalar values like I did here, just to show you the concept. In fact, it comes from a dot product. So multiply the force as a vector and multiply this dot product by the deflection as well. So it's dot delta xb sort of thing as a vector. So it's really a dot product, and hence sometimes we get positive, sometimes we get negative from this expression based on that. All right. Okay, the same thing here, like delta u theta 2 is a dot product, the torque T2, multiply this dot product by delta theta 2, and delta u at point C, also the force FC dot product by a vector delta RC. So that's this all vectors added together. This is how to use the method properly. So here it's FB dot delta XB plus T2 dot delta theta 2 plus FC dot delta RC delta RC. That's the add up to 0. So it's really, this is a dot product here, right? That's dot product. So those are all vectors, right? This or FB FB is a vector, and I just put this half arrow on top of things to remind you it's a vector. And if we look at it, FB here, it's a force, and as a force, it's a vector, and it has a length or a magnitude FB, and there is an angle 0, as you can tell, based on how I draw it here, right? And delta, right? This sort of thing. Right now, same applies, goes for FVC, and that's a vector. I can say FVC is also some FVC and EJ 3 pi over 2, right? Those are vectors, and we are clear on those, right? But then how to deal with those other displacements and the torque as well. All right, so before we do that, I'm going to divide this equation by delta t. So I'm going to say over here, I'm going to say FB as a vector dot delta XB delta t plus T2 delta theta 2 delta t, and then FBC dot product delta RC delta t, that's equal to 0. Now I have velocities instead of displacements, and we are possibly more used to this formula. So this here is going to be my vector VB, and this is FB plus T2 dot U2, that's omega 2 plus FC times velocity VC. So this is a small transformation of the equation by just dividing by delta T. So we'll move from the work Newton meter domain to the power domain. So this equation is more a power equation. So I was talking before about here, this was more like work. This was really work equation. Now this equation is more like a power equation. It is the same equation, just divided displacement by delta t. I get a power equation because we are used more to omega and some velocity terms and so on. So, okay, so now VB, as you know, I spoke about, discussed that if the forces are vectors, and I can write those vectors in this manner, sort of thing, with also complex number notation. And then the force is also velocity is also a vector, which we write in complex number notation. When I know that VB, this velocity over here, is going to be, this velocity is going to be equal to VB and some J0, right? Sort of thing, some quantity VB and J0, E to J0 to give me the direction. I'll get VB from velocity analysis, right? Velocity analysis, I get VB. And if it's, I'll just check whatever expression I get from the velocity analysis over here to get me VB, right? And can be positive or negative, whatever one you calculate, right? And VC is the same. So VC, as you get it, VC is equal to VC. This is the velocity of this point here, will be equal to, as you know, will be equal to V. Okay, just maybe we differentiate this expression here to get our VC, right? Differentiate this expression. So you get R2, differentiate. So to get here, get D, RC dt, R2 dt, plus the other expression, which is RC relative to A dt, right? C D, RC relative to A dt. And so this was here, this will give me R2 omega 2 A J theta 2 plus pi over 2, and this other term will give me H omega 3 A J theta 3 plus pi over 2, and I add them together, to get the velocity. When I add those together vectorially, I'll get at the end of this process, I'll get some quantity, magnitude Vc, and e to j, some angle, whatever the value of this angle here. Let's call it beta or phi or something, and this angle will have in it all theta 2 and theta 3 and whatever. So right, so this will be the situation here. And don't forget also, we get an expression for omega 3 from my velocity analysis. From velocity analysis, we get an expression here. So I have now an expression for also for VC as a vector. So I have VC as a vector and FC, VB, and FB. Now, how about torque and omega? So omega, we know how this is how to deal with omega and T and the torque in our equations because they are actually vectors, but they are vectors in the Z direction, right? So if this is X, Y, and this is the Z direction, and there is an omega like that, okay? So this omega is in fact a vector which is like that. This is the vector omega, right? Omega in the direction of k. That's omega as a vector. And the same thing goes to the torque. The torque also x, y, and this is z, and this here the torque is this is the torque which is T times K, exactly like omega. So we see the effect of those, of the torque and omega, we see the effect of those in the plane, like the rotational effect, but in fact they are vectors, and as vectors they are directed in the K direction. But do I have to worry much about this? I don't, because what happens is we have decided already on a convention for omega to be positive or negative, and for T as well, because T and omega will be the same. So in this case, if T is, so for counterclockwise, or this is counterclockwise, omega is positive and T is positive. And then the opposite to that here, if they are going clockwise direction, so clockwise rotation, right, T is negative and omega is also negative. And that's how I substitute them in my expression for the virtual work or virtual power. Now, if you like, I substitute them using either positive or negative values. Okay, so like in this case, in my example here, this torque will have to be positive. That's a positive torque simply because it's going in the counterclockwise direction, and omega 2 is positive as well. So normally, when I write this equation up here, I'm going to write T2, omega 2, put them on one side, and on the other side, I'm going to have minus FB dot VB minus FC dot now times or dot or whatever dot VC. I can write the equation like that, and I can say those together, they are like a load acting on the system. That's a load acting in the system, and this is the input to the system here, input power. So, and that's why we say that you'll find many people refer to this equation as power in is equal to power out, sort of thing. So that this sort of equation, power in is equal to power out, actually comes from the virtual work method. All right, but how? I need just to say, explain now how to calculate the dot product of vectors. Like if I have, right, if I have, let me give you this example. So if I have FB was some FB, right, e to j 0 or something like that, okay? Now, and then VB is as a vector, so VB was equal to, those are dot products, don't forget, of vectors, right? And those I can just remove the dot product and remove the arrows from here because I know I have a convention plus or minus for them. So VB is VB E to J 0. So what happens is the dot product FB dot VB, the dot product is simply you multiply the two magnitudes and then multiply the two magnitudes and cosine, multiply by cosine the difference between the two angles, right? So if it's both 0 degrees or whatever, 0 minus 0 is 0, cosine 0 is 1, so it's VB times FB straight like that. What about the C? So now FC times dot product VC, FC was equal to mg or some load or some force FC downwards. Let's have a look at it. Okay, so here I have the FC downwards. So over here, so FC is some quantity magnitude FC 8 to J 3 pi over T, so going downwards, and then dot VC, which is some value VC 8 to J phi, and then the magnitude is just FC times VC cosine the angle between them, pi minus 3 pi over 2, which I can simplify if I want to. So this is how we do this and that, this dot product in a plane, as simple as that. A cosine, cosine, and then plus sine, sine will be minus, right? Cosine, sine minus sine phi. This expression here, minus sine phi, just by way of example. It doesn't really mean anything, just like an example in this specific case. So that's how we calculate. So when we write our equation, will be T2 omega 2 being equal to FB VB minus FC VC cosine the angle between those two. So will be VC sine phi. So this will be my input power and this will be my output power, right? This is the idea mainly, right? This is the idea that we try to apply when we calculate the torque required. So on the motor torque, we'll find when we apply this in most cases, we'll be able to express, we'll be able to have a common omega 2 out of here and common omega 2 out of here, and then omega 2 will cancel in the whole equation, and then we'll end up with the torque being expressed as function of the forces and other things acting on the system. Normally what you need to do after that is to plot the torque required at the crank T2 against the crank angle, like from like initial, right, 0 theta initial theta 2 to theta 2 initial plus 2 pi for a whole sort of rotational 2 pi 1 rotation of the crank, and we refer to this specific drawing as or graph as this is the T theta diagram. So that's what call that. This characterizes the system type thing. This tells us how much torque is required at the crank for the mechanism to be able to rotate without stopping, and to be in the same time overcoming the load which was trying to stop it. So now let's do another quick example. If I have an example, let's do like a 4-body chain, for example. So if I have a 4-body chain like that, and this is omega 2, torque T2, and omega 4, and the torque T4 is trying to stop this from rotating. That's why we refer to this as the load, right? And this is the driving torque. So this is driving torque here. I want to write my equation. So I have my input is T2 omega 2, and this is plus T4 omega 4, that's equal to 0. And I know omega 4 is going to will have negative negative value. When I substitute over here is going to be negative when I put a numerical value here, right? So, and then you can say T2 omega 2 is equal to T4 omega 4, and then the negative value, when you transpose it to the side, is going to be positive. Now I have negative in front of that. Now, and you can tell straight away that well, so T2 omega 2, I'm going to substitute information from my velocity analysis to omega 2 is equal to minus T4 omega 4. If you remember from velocity analysis, omega 4 was equal to R2 over R4 J theta 2. Underneath here I had J theta 4 times omega 2. This was all that was in fact omega 4 from velocity analysis, and you go back to this and you'll find we've got something like that. Then omega 2 cancels out, as I said earlier. So normally you'll be able to cancel omega 2 will be as a common factor, and then you have T2 is equal negative R2 over R4 J theta 4, that's Jacobian, over another Jacobian here, which is underneath. The one underneath is my major Jacobian. If it's 0, then the crank will stop. Right, this then times T4. Okay, so all those quantities are normally, those are all sort of dimensionless quantity, and you have torque on both, on each end here type thing. So just Newton meter. Normally, this would be known, usually the load is known, and we design the linkage. Before we design it, we know that. So I do these calculations because we're not sure, we don't know exactly that kind, like how powerful the motor that's required to drive the thing will have to be. In this case, this analysis will help us make this decision. So they make, right, okay. So in any case, when I look at those together, I can tell you that when I wanted to have as small as possible T2 to drive the linkage. Don't forget that. Okay, so I wanted high mechanical advantage and I want things like that. So uh, because normally the linkage multiplies the input torque for us to give us the load to, to be equal to the load torque. So to magnifies the input torque for us. Normally, this what happens. And then if you draw, you'll find that if I draw something I want to do always when I analyze a linkage, if I have theta 2, I wanted always to draw this sort of main determinant against theta 2, and of course I want to make sure it stays on one side of the y-axis, shouldn't cross from negative to positive, otherwise it will be 0 at some point in time, and this is not good. But I also want to make sure, even if it stays all in the positive, which is great, or all in the negative, which is also great, doesn't matter. The minimum value of this is still large enough, because you see this here goes into that. So if this minimum value is small to 0, then at this specific point in time, my torque T2 is going to be high type thing. So the motor and the flywheel and everything on the crank will just struggle to provide this torque. And then when you see a linkage like this running, when you hear it running, you can hear the noise. You can tell everything is suffering to make it go type thing. Just because this is specific determinant was close to 0 at some point in time. So if this was the case, we need to go back to your linkage and try to make sure that you redesign the dimensions, and you plot J theta 2 again theta 2, and see what happens, and make sure that you have lifted this a little bit higher than 0 to make sure that you have a smooth operation for your linkage. That's an important thing. Also, if you remember, we spoke earlier about, possibly in lecture 2 or 3, about the mechanical advantage, which was equal, the mechanical advantage was equal T4 over T2, and normally you would like T4 to be greater than T2 in the thing. So you put some T2 and it will be magnified to T4 at the other end. And if you want to write an expression for mechanical advantage, you just need to go back to this equation and arrange it, and then you'll have minus R4 over R2 J theta 2 over J theta 4, and this will be my mechanical advantage, just my multiplying those. And you can tell that if J theta 4, if this is equal to 0, J theta 4 is equal to 0 when omega 4 is 0 and 4 link 4 is stationary. So at our extreme positions, right? And you can tell if this is 0, like close to extreme positions, mechanical advantage is going to be high. And that's a good thing. So normally, if the linkage is a toggle or some sort of device that acts as a vice and supposed to put some pressure at a point or a part or something like that, you can design it in such a way that when the pressure is about to be applied, this link number 4 will be close to the extreme position, and then you get a high mechanical advantage at this point. So the insight you get from these equations is quite interesting as well. All right, I'll give you another example which can be useful if you are designing a linkage. Like for example, I am mechatronics or mechanical engineers. You design, you have, let's say you have a system such as like a tray of some sort, and it's fitted here. Just that's an example. All right, so that's fitted here, and then you are going to drive this with a like sort of pneumatic or hydraulic cylinder or something. So that's so you have hydraulic cylinder here or pneumatic cylinder, and you are so that's fixed here. Let's say as well, and you are driving this with the hydraulic like cylinder, piston or whatever inside that, and then let's say you have some load acting at this point here. So if I'm going to say this here, this is just welded together, and let's say I want to drive this at some constant omega 2, but my input device is actually the hydraulic cylinder. So this is my input device to the linkage, right? Okay, but I want to drive this at some constant velocity or something like that. Now, and I want to calculate the rate at which I need to extend my hydraulic cylinder. So this will be extended at some rate, which is like sliding velocity, which will give us the required omega 2. And let's say I have some force acting at this point, also some load, FL sort of thing, like vertical, and I need to be able to provide the force, make sure my cylinder would have enough pressure to deal with this specific load, right? So I have enough pressure here or enough force. I'll need to calculate the force. So if I say this here, I want to draw a linkage as an equivalent to this machine. So I can say, okay, this here, this is fixed. This length changes. So, okay, so that's, I can then say it's 90 degrees. It's 90 degrees. I can have a slider here. I can have a slider. Hit it here and allow sliding in this direction. So sliding would be allowed in this direction. And I have my point where the load is applied here. All right, if this distance is h, this distance is, well, if it was b or whatever distance here, so the slider is fixed at a constant distance over here. And let's say, and this point here is also fixed at constant distance from the other end here, type thing. So I can now, because that's all fixed, I can imagine I have connected my, I have connected like those points or something like that. So, oh goodness. So now if I say I have, if I connect those two together, comes right, type thing. So this will give me this link here, will give me the same effect as those two. And maybe I can say this is my linkage over here. So that's like I can say that's equivalent to what I'm dealing with. So that's the linkage over here, right? So this is my linkage. And so, okay, so it becomes something like that. Just trying to just establish, put together a linkage that will simplify what I'm doing over here, right? And this point here will have the slider connected, and a sliding is going to occur in this direction, a sliding direction. So I can say this is this distance here is L, for example, and this is F. So this is point A, this is B, so that's B, so FB type thing. All right, and now I have my axes. So I have my x-axis here, I have my y-axis here. So, and I can say this is my theta 2, and this is another constant angle here. We call it phi or anything like that. It's an angle phi. That's not a problem because I need it later on to find velocity of B. So this is R. I can say this distance here is R3. This is R3, and hence I have R. This will be R2, vector R2. That's an R2, and then so R2 as a length. R2 as a length. The length of R2 is, I'll write this as small r2. R2 is the square root h squared plus b squared. This is the length of R2. So this is R2, vector R2. R2 is equal to R2 a to j theta 2, and I'm measuring theta 2 from this fixed. This line is fixed on the link anyway, on my tray type thing. So this here is my theta 2. And okay, I have R3, which is this here is R3, right? So R3 is a variable length R3, AJ theta 3. It is variable because the hydraulic cylinder extends in and out. So the length is variable, and I can say I have R1 as well here. That's R1, and R1 is 0 e to j pi, or no, I mean the length is not 0. Length R1 is R1. So it's R1, R1, length R1. Here, write this in over here in red. So that's length R1, and the angle of R1 with the x-axis is equal to pi. Then if I do my loop closure equation, I have a loop over here. If I add those two, will give me the one that will close the loop, which is R2. So I have then R1 plus R3 is equal to R2. That's a loop closure equation. I can write it in the polar form, J pi plus R3, which is R3 AJ theta 3 is equal to R2 AJ theta 2. And then I can find from this equation relationship between my different, uh, if you like, my different coordinates, or my different position of different links as function of theta 2 if I want to. So if I just go real and imaginary, so the real will give me R1 will be negative because cosine pi is -1, plus R3 cosine theta 3, that's R2 cosine theta 2, and the imaginary cosine sine pi is 0, so I'll get R3 sine theta 3 equal to R2 sine theta 2. This is supposed to be theta 2, and then I can get rid. I have two, and like my unknowns are R3 and theta 2. Those are my two unknowns, right? And I have one loop closure equation gives me two scalar equations I can solve together. So I can rearrange the equation here. I can say that's R1. I can move R1 to the other side of the equation of the scalar equation. So I have R3 cosine theta 3. This will be equal to R2 cosine theta 2 plus R1. Then I can square and add. So I call them 1 and 2, square 1 and 2, and add them together. When you do that, you get on this side here R3 squared, and then in brackets you should have sine squared and cosine squared, they add up to 1. Over here I square and add, I'll get R1 squared plus R2 squared plus 2R1 R2 cosine theta 2, and this tells me that the length of the cylinder at any value of theta 2 is equal to just square root of R1 squared plus R2 squared plus 2R1 R2 cosine theta 2. So against any value of theta 2, I should be able to get the length of the cylinder that I want to achieve. And that's a control problem now because you are driving the cylinder. You want to drive the cylinder in such a way that it extends in a way that will match the required value of theta 2. Then if you wanted to calculate also the rate at which the cylinder is going to extend, you need to differentiate your loop closure equation over here. So you'll get, if you differentiate this, I'll write the loop closure equation again one more time for you. So R1 AJ pi plus R3 AJ theta 3, that's equal to R2 AJ theta 2. And then if I differentiate that, I get 0. This here, I have two variables, both R3 and theta 3 are variables, which means when I differentiate, I get two terms, the sliding term in the direction of theta 3, and then the one perpendicular to the link R3, which will be R3 omega 3 e j theta 3 plus pi over 2. On the other side, I have R2 omega 2 e to j theta 2 plus pi over 2. And then when I go real and imaginary over here, I'm going to do, if I do real, which is the cosine term, I get Vs cosine theta 3 minus R3 omega 3 sine theta 3 being equal to minus R2 omega 2 sine theta 2. And then the imaginary term will give me Vs sine theta 3 plus R3 omega 3 cosine theta 3, that's equal to R2 omega 2 cosine theta 2. And then I can arrange this equation here. I can have Vs, I can have R3 omega 3, and on the other side, I can have a common factor R2 omega 2, and I can go Vs, that's cosine theta 3, and here minus sine theta 3. On the other side, I have minus sine theta 2, and here I have sine theta 3, cosine theta 3, cosine theta 2, and this is theta 2, and then this here will be the main Jacobian, the system cosine, this is j theta 2, right? And then if you wanted, so j theta 2 is equal to cosine theta 3 minus sine theta 3 sine theta 3 cosine theta 3, and when you add those together you get 1, correct? You get 1, and then no, but in fact, yeah, what I should do is to say when I calculate the determinant of the j theta 3, I'll get 1 because I multiply cosine square plus sine square, I should get 1. That's how I should write this in a proper fashion, otherwise it will not be right. Then I have j theta 3 if I want to, which the same determinant, but multiply the column, second column here, replace it by the column on the right hand side. So you get cosine theta 3, sine theta 3, and then the other column here is replaced by sine theta 2 and cosine theta 2. And then if you want to calculate the Jacobian over here, which will give you cosine squared plus sine squared. So you get this Jacobian now will give you, if you calculate cosine squared plus sine squared, will be cosine the difference. So cosine theta 2 minus theta 3 if you like, or theta 3 minus theta 2, doesn't make much difference. And then if you want J R3, and then you replace the first column by minus sine theta 2, cosine theta 2, and the other side here you have minus theta 3, cosine theta 3, and then the determinant of this specific matrix is equal to, multiply those together, and you take away those together, so you get the difference between the two. So this will be sine theta 3 minus theta 2. Okay, because this will be positive and this will be negative. In fact, I'll go back here and write this theta 3 minus theta 2. It does not matter cosine, because cosine theta is equal to minus cosine minus theta is equal to cosine theta, so it does not matter. But over here, I just wanted to have a formula that looks elegant. So theta 3 minus theta 2 in both expressions. So now this tells me that, like omega 3, if I wanted omega 3 R3, so that I'm going to write this expression of like the proportionality, the ratio expression. So omega 2 R2 on J theta 2 is equal to omega 3 R3 over J theta 3 is equal to V sliding over J R3, determinant of JR3. Okay, JR3. So this one, omega 2 R2 over 1, so it's 1 underneath, that's equal to omega 3 R3 over cosine theta 3 minus theta 2, that's Vs over sine theta 3 minus theta 2 from what I've just done here, right? And then I can write that omega 3 is equal to omega 2 R2 over R3 times cosine theta 3 minus theta 2, and V sliding is also a function of omega 2. So it's omega 2 R2 sine theta 2 minus theta 3 minus theta 2. So I have expressions for the velocities as function of theta 2. Now, if I wanted, so as if you need to be able to control the rate at which the hydraulic cylinder extends to match this equation, right? Sort of thing. So you can plot this against theta 2, Vs, whatever you find, this will give you what you need to apply at the hydraulic cylinder end to be able to create the linkage, that you drive the linkage in the fashion that you wanted, type thing. So that's really more of a control problem at this stage, because you feed whatever pneumatic air or hydraulic fluid into this via a control system, some valves, directional control valves and whatever, and pumps and whatever, just to give you the rate of extension that will make omega 2 happen at this specific value. And this rate of extension is function of the angle of the tray as per this equation, right? Don't forget the theta 2 itself is function, theta 3 is function of theta 2 as well from the position analysis, right? So, and we can write this expression here if we wanted. So like we can get theta 3 from here if you like, right? So theta 3 can get from, like you can say, cosine theta 3 is equal to R1 plus R2 cosine theta 2 on R3, and then they put this expression under this the R3 thing, and you can go theta 3 is cosine minus 1 R1 plus R2 cosine theta 2 over R3, and you have your theta 3 as function of theta 2, and then the theta 3 which goes into here, so you can plot your expression for Vs against theta 2 and try to apply in practice. Now, what sort of pressure I need in my hydraulic cylinder or pneumatic cylinder or whatever I want to use over here? So I need then to write use my virtual work method to write my equation. Then I have the forces I have. Okay, maybe I'll just plot this one more, draw here one more time quickly. Then I remember it was something like that, something like that, something like that over here. And then there was like a slider of some sort headed here, and then which represented the hydraulic cylinder. Hydraulic cylinder was here. Then I have some force acting over here. Okay, and so this point, call this A, this is B, and there was some force acting FB, right? It can be a constant load or like whatever. So, okay, so now FB is as a vector, it's FB A to J 3 pi over 2, that's the direction. Then I need VB as well. So VB as a vector is equal to, if this whole length is L, so it's really equal to, okay, I need to, it will be then equal, and this angle here, was it called phi or something? That's phi, right? So just go back, check what I called it before. So now this angle was phi, okay, call this phi. All right, so that's fine. Then I'm going back here. I'm going to write the way I get my VB, just to explain it to you a little bit more. I'm just going to say if I have RB, RB is L A to J theta 2 plus phi, which is constant. This angle here was theta 2, right? So then VB, I need to differentiate that. So get L omega 2 E to J theta 2 plus phi plus the 90 degrees rotation that I'm talking about. So now if I go VFB dot VB, I know what to do. I just sort of multiply FB L omega 2 and then cosine the angles between all those. So theta 2 plus pi over 2 minus 3 pi over 2, which is equal to FB L omega 2 cosine theta 2 plus phi minus pi. So when you do that, that's cosine. So I'll give you minus FB L omega 2 cosine theta 2 plus phi. Cosine theta 2 plus phi. This is one equation here. And then, because when you expand this term, cosine that, cosine phi is negative 1. So it appears in here. Right. The other force I have is FB. So, and this is, and Vs, right? So FB as a vector, this vector FB, don't forget theta 3. So FB is directed along the cylinder here. It's force coming from the cylinder. So it's FA, isn't it? Sorry, FB was at the other end. It was I call this FA, right? So FA is some force as a vector, some force FA, E to J theta 3, because directed along the hydraulic cylinder. And VS is VS, right? E to J theta 3 as well. I can put little arrow just to say the vector VS. Now, and those together, if multiply them, will give me the driving power. So I have FA dot Vs. This will be FA Vs cosine theta 3 minus theta 3, which is 0. Cosine 0 is 1. So it's FA times the velocity Vs. Now my virtual work method equation would say FA dot Vs plus all the virtual little infinitesimal work add up to 0 it is. So then FB dot VB, that's all this stuff adds up to 0. FA, this term we just discovered, it's FA times VS plus, so that this will be negative over here, FB L omega 2 cosine theta 2 plus phi, that's equal to 0. Okay, that's equal to 0. And in this case, I can just rearrange my equation to get an expression for I get FA. And here I have VS on the other side, that's FB L omega 2 cosine theta 2 plus phi. And then what happens here is I will have cosine Vs. I had an expression for Vs as a function of omega 2 from before, and this expression will actually here it's omega 2 R2 sine the difference between, so it was, and then multiply this by omega 2 R2 sine theta 3 minus theta 2, that's Vs, all this is Vs, that's equal to FB L omega 2 cosine theta 2 plus phi, and then omega 2 cancels out. You get then FA being equal to FB L cosine theta 2 plus phi over R2 sine theta 3 plus theta 2 or something like that over here, this expression here, right? This was theta 3 minus theta 2 sine. Okay, so this will give me an expression for the force required in the cylinder. And if I say this force is actually, if you divide this force by the area of the cylinder, I'll get the pressure that needs to be realized inside the cylinder. So you get then the pressure inside the cylinder is supposed is equal to FA over pi over 4 d squared. This is the cross-section area of the cylinder. Then you get all this expression and you end up with the pressure of the cylinder against theta 2. And you see, you need to look at this curve and see how much the maximum value of this pressure is going to be such and such. Then when you design your system, you make sure that your pump or whatever you have, compressor, whatever you have in the system, if you use pneumatic or hydraulic, will be able to provide this pressure for the system when it needs it. All right, so this is the end of this lecture. We'll try to finish the position analysis next time by looking at the graphical method. All right, okay, thank you.